Let's graph another polar equation. This one's r squared equals 4 sine 2 theta. Maybe you guys have gotten enough practice right now to kind of guess what we're going to do or how to proceed. So what should we do first? Okay, let's test for symmetry. And how do we do that? Well, let's begin by testing for symmetry about the polar axis, which means that we replace theta with a negative theta. All right, I'm with you. Okay, you're right. Sine was an odd function, which means I can rewrite this the same thing as r squared equals negative 4 sine of positive 2 theta. And what do you notice? You notice that it does not match the original equation. So when it doesn't match, it fails a symmetry test. But just because it fails a symmetry test does not necessarily mean that there is no symmetry about the polar axis in this particular case. All right, what do you want to test for next? You want to test for vertical vertical symmetry. All right, so we do that by inputting in a negative r and replace the theta with a negative theta. Solve that out. Negative r squared becomes r squared equals negative 4 sine of 2 theta. What do you notice? That one doesn't match either, so it fails the symmetry test about the vertical axis. And let's test the last one where it's about the pole. So we replace r with a negative r and keep theta the same. Negative r squared becomes r squared. And we get our original equation, so that does pass the symmetry test about the origin. Failed along the polar axis, failed along the vertical axis, passed along the origin or the pole. So we are going to expect symmetry at least to occur in one part of the function. So let's go ahead and get our graph paper ready so we can go ahead and start to plot some points. Which points do you want to check? All right, so which values did you choose? Notice I only chose values in the first quadrant to test. And the reason why? Well, I know it's symmetrical about the origin. So any value I get in the first quadrant will be reflected in the third quadrant. So I know that all my values here will have a plus or a minus component to that. Because again, what value in this direction is going to produce the opposite value because it's symmetrical in the opposite direction. So I'd have an r and a negative r. Let's plot some of those points. 0, 0. On the pi sixth angle, I'm at 1.9, 2, and 1.9. I know it's symmetrical, so I have points on the other side as well. Go ahead and gently draw a nice curve that kind of catches those points nice and easy. All right, there we have the complete graph of r squared equals 4 sine 2 theta. Complete graph? Well, how do you know that, Willie? You only checked values in the first quadrant, and I buy the fact that it's symmetrical about the origin, which means that we have values in the third quadrant, but you didn't check anything in the second or fourth quadrant. What gives? Well, as you get more practice that, you're going to look for some shortcuts or some things that might be a little clever for you to think about. So let's just imagine for a second, based on our original function that we have here. Notice that I have twice the angle. So imagine then that if I had some angle over here in the second quadrant, like 2/3 pi or whatever it might be, but some angle that is expressed into the second quadrant. So what happens when I double that angle? Well, it's going to come down either into the third or fourth quadrant. And what do we know about the signs of functions in the third and fourth quadrant? Are they positive or negative? You're right, those are negative. And then I look back at my original function that says r squared equals, if that's the case, some negative number. Can I have a square from a negative number? No. Or I guess I said that backwards, but can I solve this in some type of way where I get some r or take the square root of a negative number? I can't within a real set of numbers. So what that tells me then is that any angle that I look for in the second quadrant and double it, it's going to produce a negative sign. And I can't take the square root of a negative sign. Likewise, that will happen in the fourth quadrant. If I took any angle in the fourth quadrant and doubled it, it will again show up in a quadrant where I cannot use a negative sign or take the square root of a negative sign. So if you remember that or played with that or understand that type of an idea, that helps you realize that you don't have to choose all the other points. So to fully graph this particular graph, I just needed to graph 5 points, realize that it was symmetrical about the x or about the origin, which allowed me to double the amount of points. And then if I realized that if I had to graph any point in that second quadrant and double the angle, by knowing that the double the angle will produce a negative sign and I can't do an r squared equaling a negative, I didn't have to choose those points either. But you're more than welcome. You're more than welcome to choose these points, find out their values, and you'll find out that the calculator blows up and doesn't work. Anyway, I hope this has been kind of fun. And another family that we have of graphs, of polar graphs, are lemniscates. And we see two different forms right here. One where we have an r squared equals an a squared times the cosine of 2 theta. And you notice that it follows along as symmetrical about the polar axis. And then we have one that's symmetrical about the line y equals x, or the line theta equals pi fourths, where r squared equals a squared sine of 2 theta. So these are what we notice and are called our lemniscates.